I'm glad that Rajiv has already introduced the distinguished speaker. So I will introduce myself. I am Rajashekaran from Chennai, a high energy physicist. So now I request Professor Chan Joshi to start the talk.
Okay, thank you very much. First of all, thank you everyone and the organizers particularly for inviting me. I saw the program and the distinguished list of speakers you've had, and I understand that this is probably your last day. Is that correct? So I hope to give you a different flavor about where we are going with respect to the plasma acceleration work in the United States. In particular, I'm going to focus on Plasma-Wakefield Accelerator Program, that is the beam-driven plasma accelerator. But much of what I say is common to both laser and beam-driven plasma accelerators. And the theme of my talk basically is, the scientific theme, is how the processes of beam loading the plasma wake to extract energy from it and beam matching are essential for obtaining both high efficiency and small energy spread, at the same time preserving the low emittance of the beam. These are all necessary conditions for application of a plasma accelerator to both a collider and possibly a future light source. How is this not moving forward? Can you go to the next view graph, please?
Yeah,
are you on the next view graph?
Yeah, it is on the next slide.
One moment though, hang on. I need to get my PDF. Okay, so can you still hear me?
Yes.
Okay, so the next view graph shows basically who we are, just in case there are some people who don't know. The UCLA program on plasma-based accelerator is headed by myself as an experimentalist, and Professor Warren Murray, who is the theorist and simulationist. I understand that he gave you a talk yesterday. And this was basically the first group working on plasma-based accelerators pretty much in the whole world. We started our work in around 1982. But right now, we do work in all three areas of experiments, theory, and simulations. And in addition, we have collaborations at Livermore, SLAG, IST, LLE at Rochester, and Tsinghua University in China. Next view graph, please.
Yep.
Okay. Now, just to quickly tell you, these are just some of the alumni. That is, since we were the first group, many of the students and postdocs we trained went on to form their own groups in different universities and institutions in both the United States and all over the world. And these are just some numbers, some names that came to my mind up to 2011. So since then, there have been many other students who have gone on to form their own groups or working actively in this area. But you'll recognize many of the names: Tom Katsules, Warren Murray, Wim Leemans, Chris Clayton, Don Umstatter, Dan Gordon, Patrick Mugli, who's at CERN, Sergei Tochis, Wei Lu. There are lots of people. Okay. Next view graph, please.
Yep.
Okay, so let me quickly recap that there were many experimental firsts done by the UCLA Plasma Accelerator Group, and much of plasma accelerator theory was also done within our group. Let me quickly tell you that, for example, the whole thing began in 1981 with a paper that I wrote on electron acceleration by Raman forward scattering, which later on came to be called self-modulated laser Wakefield accelerator. In 85, we showed that beat wave excitation was an effective method of exciting relativistic electron plasma waves. In 1993, we showed that the beat excited relativistic plasma waves could accelerate externally injected electrons. Then we showed that these electrons could be trapped by the wave and accelerated to very high energies, up to 30 MeV in a centimeter. In 94, we showed that plasmas can be used for focusing relativistic electron beams. In 98, we showed that electron gain in a plasma wave can be beyond the linear dephasing limit. Then in 2003, we showed acceleration of a positron by Wakefields in a plasma. We also showed time-dependent focusing of positrons by plasma lenses. In 2005, we showed we broke the 1 GeV barrier using a beam-driven plasma Wakefield. In 2007, we showed that in a meter-long plasma, you could gain 42 GeV energy in less than 1 meter. And so this was demonstrating that you can get energy gains of interest to high-energy physicists. And in 2011, we showed it's possible to make a staged laser plasma accelerator. So these are just some of our achievements. And since 2011, there have been many, and I'll just talk about them. Next view, please.
Yep.
Okay, so the outline of my talk is I'll quickly say what a plasma Wakefield accelerator is. I'm sure that most of you know what it is. Nevertheless, it is important to say that as a baseline. I will explain what major milestones have been reached. Then I want to talk a little bit about the Department of Energy's strategic planning report for Plasma-Accelerator Field. And then I want to talk about the first experiment that we have planned on a new facility that is being built in the United States called FACET 2 that is aligned well with the DOA's strategic plan. And then I'll say about what we need to do to get there. So most of the work on plasma Wakefield accelerator, next view, please.
Yep.
Is done using the linear accelerator at Stanford. And the reason for that is because the beam powers contained in both electron and positron beams at the Stanford Linear Accelerator are comparable to the highest power lasers that we have today. Plus, the beam repetition rate is 10 to 60 hertz, so you can get a large amount of data and you can aim for reproducibility of experiments. Just to give you some idea, a typical electron or positron beam contains 1 to 4 times 10 to the 10th particles, so many nanocoulombs. It has energy between 20 and 45 GeV, rep rate up to 60 hertz, energy per pulse, which is 40 to 320 joules, and this can be focused down to 10 to 30 micron spot size. Actually, for high-energy physics experiments, they focus it down to a micron. And the pulse can be compressed down to 50 femtoseconds, or 4 picoseconds. And the focused intensity, when you focus this beam down, is on the order 10 to the 19th, 10 to the 21 watts per square centimeter. So it really is comparable in terms of energy density to petawatt class lasers focused to a few micron spot size. Next view, please.
Yep.
Okay, so I'm going to show results from both single. So let me explain what a single bunch plasma accelerator is. It is shown on the top. Basically, a single longish electron bunch passes through the plasma. It produces a charge imbalance in the plasma. The bunch is relativistic, so it's very stiff. Plasma electrons are thermal, they're soft. So the electron bunch repels via space charge the plasma electrons, blows them out, and if beam density is larger than the plasma density, leaves behind a region of pure ion column. The plasma electrons that are blown out are attracted back by the focusing force of the ions, and they cross the axis and go into an oscillation, producing a wake. Now, in a single bunch, basically, the front of the bunch, in blowing the electrons out, lose energy, but the field reverses sign at the back of the bunch, and therefore the particles in the back of the bunch gain energy. And that is what's shown on the right-hand side and it says FFTB because those results were obtained at FFTB, where the 20 GeV beam at 20 GeV lost energy down to 14 GeV, and then a thin streak of electrons have gained energy up to 40 GeV. Now, in two-bunch experiment, what we want to do is we want to send a short bunch that will act as a drive bunch to excite the wake, and then a distinct second bunch called a trailing bunch that will be placed in just such a phase to gain energy from the wake. And you can see sort of a synthetic data that, in other words, that is the data that was, it's experimental data, but that's manipulated. That's why it's fake, it's not real. That is what we hope to see. You'll see what we actually saw. We saw pretty much exactly that. You hope to see that the drive bunch, which is at 20 GeV, will lose energy. And then the trailing bunch, which was also at 20 GeV, now has distinct gained energy, and it has a narrow energy spread. Next one, please.
Yeah.
Okay,
Yeah.
so let me show you the main result obtained with a single bunch. This was done with a 42 GeV beam. And the beam, you can see on the left-hand side, which says experiment, the beam initially was at 42 GeV, that's the red blob. And after it was sent through the meter-long plasma, it was 85 centimeter long plasma, some particles in the tail of the beam were pulled out and gained energy up to 85 GeV. So that was a very, very significant result. It was published in Nature and on the front cover of Sun Courier. So high energy physicists really took notice of this. All right, next view graph, please.
Yep.
So after this result was obtained, the Department of Energy and high energy physics labs immediately said to us, well, that is really interesting, but can you send a distinct trailing bunch and accelerate it and obtain a very narrow energy spread, maintain the narrow energy spread of the trailing bunch. So the goal here basically was to send a drive bunch which had sufficient charge to produce the wake in the blowout regime, make sure that the density is large enough to produce gradients that are 5 to 10 GeV per meter, and then put a trailing bunch, which is the second bunch, at the back of this wake, and if it has sufficient charge and certain shape, basically it will load the wake. That means it will flatten the electric field of the wake, which is shown below in the red. So you can see that the loaded wake, the accelerating portion of it has a flat region at the back, where now that all the particles or most of the particles in the trailing bunch see a constant electric field as they propagate with the wake, and therefore they gain the same amount of energy, maintaining the narrow energy spread. So the idea of beam loading is critical to obtaining narrow energy spreads, as well as obtaining high efficiency, because efficiency basically is the energy lost by the drive beam to the wake, compared with the energy gained by the particles in the trailing bunch. So you want the electric field, the accelerating electric field, to be loaded to about the same level as the peak decelerating electric field. Next one, please.
Yep.
Okay, this one shows then the results, and basically these are 4 shots, 4 distinct shots, but there are hundreds of these. In the bottom right-hand corner, you basically see when there is no plasma and the beam is just, the 2 beams are sent through, on the spectrometer, they're at 20 GeV, they're right on top of each other, okay? And it's slightly, the screen is blooming, it's not really that wide. And then when the 2 beams are sent through the plasma, separated by only hundreds of microns, these are, remember, these are 20 GeV beams, and I won't explain how that was done. But when they're sent through the plasma, you can see now the 3 shots, and they'll pretty much look the same. The drive beam at 20 GeV has lost energy whereas the trailing beam, which was also at 20 GeV, now has gained energy about 2 GeV. And you can see sort of the reproducibility of the data. And in the paper in Nature, there are 100 shots plotted in a row, and they've been sorted out by the charge in the trailing bunch to demonstrate beam loading. So this was also published in Nature. The key thing was that this time we showed that instead of just a few electrons in the tail of the dry bunch, we could accelerate 90 picocoulombs of charge in the core of the trailing bunch. That's the blob that you see at the top. It was 5 GeV per meter, which is plenty for the high energy physicists, by the way. And the key breakthrough this time was that the energy extraction efficiency was up to 30%. So this is the first time we or anybody had shown that accelerators can have high efficiency. About 10% efficiency is needed to build the next linear collider. Just to give you some idea, the Stanford linear accelerator's efficiency is 10 to the minus 4. So we've gone from 10 to the minus 4 up to 30% efficiency. So that is a major, major accomplishment. Next one, please.
Yep.
So some of the other accomplishments of the E200 collaboration, which is our major experiment for which I'm the principal investigator. So in the last 5 years is that what we did for electrons, we also managed to do with positrons, where we found a new regime for positron acceleration, which I call the pi pulse experiment, by analogy to atomic physics, where the front of the bunch loses energy in exciting the wake, but the back of the bunch gains energy as it takes energy from the wake. The difference being that this transition from the front to back occurs right in the middle of the bunch. So a significant amount of charge gets accelerated, and so you basically get a single bunch splitting into two. We also showed that we could map the longitudinal and transverse wake fields of the wake and demonstrate that the Panofsky-Wenzel Theorem, which is a critical theorem in accelerator physics, which says that the longitudinal variation of the focusing force is equal to the radial variation of the accelerating force. And so this is a critical theorem in accelerator physics. It holds to a very high degree of accuracy for plasma accelerators. And it is important later on, as we will see, for maintaining the low emittance of the beam. We also showed positron propagation, wake excitation, acceleration, and transverse instabilities in a meter-long hollow channel. So that was published in Nature Communications, and another couple of papers are coming out in that. Okay, so following all these results, next one, please. Yep. Does this say general consensus?
Yep.
Okay, general consensus on what the AAC, Advanced Accelerator Community, should do has been reached. There were several high-powered committees, the SNOWMAS 2012 effort, which was the entire high-energy physics community, HEPAP, which is the High Energy Physics Advisory Panel, the P5 committee, that is a Particle Physics Priority Panel, the GUARD committee, subpanel. They have all urged DOE, high energy physics, to plan a coherent advanced accelerator research and development strategy with the linear collider at the energy frontier as the ultimate goal. And so DOE has to follow all this. So as a result, the DOE did an extensive study and came up with a 10-year program for plasma-based accelerators. And I'm here going to concentrate on plasma Wakefield accelerator. And basically, the 10-year program for plasma Wakefield accelerator says that the two areas of beam plasma physics, oh, next one, please, I'm sorry.
Yep.
Does this say 10-year program?
Yep.
Okay. The two areas of beam plasma physics considered most pressing for research in the next decade are emittance preservation and positron acceleration. I'm not going to talk about positron acceleration in this talk at all. And additional priorities include beam loading, high transformer ratios, beam dynamics, tolerances, plasma source development, staging, and off-ramps. I'm going to talk about everything that's in the red. Next one, please.
Yep.
Okay. So DOE is, to enable doing this, DOE is building a new facility called Facet 2, and it is our collaboration's goal to propose a major experiment that is consistent with DOE's one or more strategic goals that I just talked about. So we have come up with an experiment, and that experiment, we are hoping to take the drive beam, a 10 GeV drive beam, and deplete it completely of its energy. We want to show that we can extract 50% of the drive beam's energy into the trailing beam while maintaining less than 1% energy spread. So we've already done 30%, so we think we can do 50%. We've done 2% energy spread. We want to go to less than 1%. We want to show that the trailing beam can gain 10 GeV energy gain. We want to minimize the energy spread. I already said that, less than 1%. And the main thing is that we want to demonstrate that the emittance of the trailing beam can be preserved. So this is the first step towards eventually getting a collider quality beam that has to have sub-micrometer emittances. Next one, please.
Yep.
All right, why is this experiment realizable on Facet 2 and wasn't realizable on Facet 1? The reason for that is the key, here are the parameters for the beam parameters for Facet 1 and Facet 2. The drive beam energy for Facet 1 was 20 GeV. For Facet 2, actually, it's going to be 10 GeV because we want to lose all 10 GeV to the wake and gain 10 GeV in the second beam, in the trailing beam. The key thing is that the normalized emittance of the Facet 1 beam was rather large. It was 20 by 100 microns, whereas in Facet 2, it will be 3 by 7 microns, so it will be extremely small. So we can focus the beam to very small spot sizes that is necessary for matching the beam. I'll talk more about that in a minute. Matching the beam to the focusing force of the plasma. So it will propagate as if it's propagating in a fiber optic, a laser beam propagating in a fiber optic. So as without any expansion, essentially, or without any oscillation of its spot size. The trailing bunch parameters are very similar. We're shooting for small energy spreads, and we're shooting for higher energy, higher efficiencies, and we want to show emittance preservation. Next one, please.
Yep.
Now, why do we think it can be done? Because we already have done little aspects of this experiment, all the aspects of this experiment, and I'll quickly go through this. Here's an experimental result that shows that we've already accelerated 100 picocoulombs of charge with 5% energy spread and 30% energy extraction efficiency with an energy gain of up to 9 GeV in 1.3 meters. So this is already in Facet 1 experiment. So now we're trying to gain about 9 or 10 GeV. We're trying to accelerate about the same amount of charge. We want to increase the efficiency from 30% to 50%. So we want to optimally beam load the wake, and we want to, so we think we can do this because we've already done 9 GeV in this game. Next one, please.
Yep.
Okay, we have shown, this was in a paper in Nature Communications, we have already shown that the field structure of the wake, the longitudinal field structure of the wake, and the transverse focusing field of the wake is ideal for preserving emittance. Here, for example, to concentrate on the bottom two the longitudinal field. In the blue, we see the longitudinal accelerating field, and in the dotted red, you see the focusing field. And here you can see that the focusing field is uniform once all the electrons are blown out. And that is essential so that all the slices of the beam see the same focusing force, and therefore they have the same phase advance if they do any oscillations of the envelope at all. If you look at the transverse field, in the blue you see that transverse distribution of the accelerating field, it is uniform. That means all the particles in one slice, irrespective of their transverse positions, gain the same energy. And you see the focusing force is linear, and therefore the emittance of the beam particles will be preserved. Next one, please.
Yep.
We have even shown that by taking an unmatched beam and focusing it to the plasma, and by varying the plasma density, we show that initially when the beam is not matched, the beam envelope as measured on the screen outside of the plasma oscillates until the plasma density is such that the plasma focusing force exactly compensates the emittance force that diffracts the beam or diverges the beam, and then the beam comes out without any oscillations of its envelope. In other words, it's guided as if an optical beam is guided by a fiber optic. So we know that the beam matching works. Next one, please.
Yep.
Okay, so how are we going to do matching? Well, you can see here the basic idea of matching. This was published by Xin-Luke Su and our UCLA group in Physical Review Letters. It's an important paper. And you can basically see the plasma accelerator called PA, the focusing force is too high and no magnetic optic, shown here by the beam focusing element, can focus the beam with a beta, that is the beta star, which is the Rayleigh length of the beam, small enough to match the plasma focusing. Okay, and in other words, there's a mismatch, and therefore what you have to do is add a matching section, which is also a plasma, which basically adiabatically drops the plasma density from the high density to a low density, so such that at the beginning of the plasma matching section, the focusing force is small enough that a beam focusing element, a magnetic beam focusing element, can focus the beam at the entrance, and then the beam is adiabatically further focused into the plasma. That's called matching. Next one, please.
Yep.
This one basically is a output from theory, and I don't have time to show you how I got the result, but this shows the tolerance of the beam matching. What happens if you're not beam matched? Basically shows the final emittance compared with the initial emittance, epsilon F over epsilon I, as a function of the beta of the beam compared with the beta matched of the beam. So obviously you want to be at 1, because then there's no emittance growth. The final emittance is the same as the initial emittance. And if you are mismatched by a factor of 2, that means beta is factor of 2 larger than the matched beta, the emittance is beginning to grow, and if you are smaller, then emittance is going even faster. Now, you might say, well, that's not too bad, but the high-energy physicists are very finicky, and they want really as little as possible emittance growth in 200 of these stages. So each stage, if it starts adding factor of 2 emittance growth, then you can imagine it's going to be, it's not acceptable to them. Okay. Now, this is where the PDF is going to have a problem. Next one, please. Next one, yeah. So next one shows QuickPIC Simulation. It's actually a movie, and you cannot see it, but it shows one of the frames from the movie, because it shows basically a QuickPIC simulation with optimal beam loading. And you can see that the first bunch has produced a wake, and the beam density is larger than the plasma density, so the wake is in a complete blowout regime. And the second bunch has flattened the wakes, so it has loaded the wake, you can see, and the beam loading is almost, you can see, for most of the beam particles, they're going to see a uniform electric field and therefore gain the same energy. And if you were able to see this movie, you will see that from beginning to end, the picture almost doesn't change. You can't discern that the beam is propagating through the plasma. And that shows that the beam is perfectly matched to the plasma. Next one, please. I'm sorry you can't see this movie.
Yeah.
Oh, you can't see this movie either. This shows energy evolution of the two bunches. And if you could see this movie, what you see basically is the vertical axis is gamma and horizontal axis is kpx c, which is the normalized distance. And the first bunch is at 10 GeV, and there is a second bunch at kpx c of 6. And if you run the movie, you see the first bunch goes down to 0 energy, and second bunch increases to 20 GeV, or gamma 4 times 10 to the 4th, with very little energy spread. Okay, next one, please.
Yep.
Okay, so how do we design a matching section? You design the matching section by working backwards. So let's look at the little sketch I've shown down there. So there's a plasma accelerator showing PA. So you start from the plasma accelerator, and the focusing force of the plasma accelerator can be represented basically as a dipole focusing, and it has a matrix element given at the top there. Okay, m equal to cosine root kappa L, etc. Okay, so we basically take the Courant-Schneider parameters for the beam, alpha, beta, and gamma, and follow them backwards through the matching section to find out what kind of focusing element is needed to match to a particular focusing section, okay? And so it is a little bit like ray optics in optics, where the slope and height of the ray at plane 2 is found from slope and height of the ray at plane 1 by the ABCD matrix, okay? Except this is a 3x3 matrix. Okay, next one, please.
Yep.
Okay, there are various density profiles we tried. They're basically incomplete gamma functions of high order, and they're shown both on a linear scale at the top and a log scale at the bottom. And really, we have to use the log scale for the simple reason you have to worry about density dropping from uniform density, which is the maximum density, to several orders of magnitude smaller density, because the focusing force of the plasma is incredibly strong, and it is significant even if the plasma density has dropped by a factor of 3 orders of magnitude. The incomplete gamma function is represented here by a scale length, which is the same as scale length defined in plasma physics, of various lengths, starting from about 2.5 centimeters to 18 centimeters. Next one, please.
Yep.
All right, so here I show the beam parameters used for designing of this 10 GeV beam, 15 kiloamp current, normalized emittance of 10 microns, 15 micron or 50 femtosecond bunch, and spacing between the drive bunch and the trailing bunch, 150 micron or half a picosecond. And the trailing bunch is, just concentrate on the black, 10 GeV. It has a 7.5 kiloamp current, 10 micron emittance, and it has 8 micron RMS width. Next one, please.
Yep.
Okay, this is a very busy view graph. I apologize for it. And in fact, I'm going to skip. Next one, please.
Yep.
Okay, so let me just show you a scenario for matching the beam. So this view graph you've seen, the picture you've seen before, but now there are some numbers at the back. So we're going to start at the plasma accelerator. And if you go to the bottom, you see that the beta function of the beam inside the plasma accelerator is only 0.53 centimeters or 5.3 millimeters. Okay. and the match beam size is 1.6 micrometers. Now, we cannot get such small beta functions nor such small spot sizes using conventional magnetic optics. So we add this matching section. And when we do that, then you can see adiabatically this red, work backwards, the red envelope is expanding. And now the beta star at the entrance here of the matching section is 3.9 centimeters. And the spot size is 4.4 millimeters. And now if a focusing optic, which is put 2.2 meters away, and the beam size of 260 microns on the focusing optic can, and if the emittance is 10 microns, it can focus the beam to this beta star of 3.9 centimeters and a spot size of 4.4 microns. The red numbers are the opposite. When you want to exit from the plasma, what you have to do to match, what kind of matching section you need to preserve the emittance. Okay, next one, please.
Yep.
So matching is possible for a whole variety of density profiles once you develop a protocol of how to do it. And so now that we know how to think about it, we can develop matching playbook for the density profile that we actually have in the experiment. Next one, please.
Yep.
Okay, now why do we choose 10 micron emittance as a starting parameter? It is because with our magnetic spectrometer, we can measure tens of % of change in the emittance of the beam as long as the beam emittance runs. So here are a series of curves that show what the accelerated beam spot size looks like as a function of energy at 20 GeV. So horizontal axis is 20 GeV, and it has a window of 1 GeV plus or minus half a GeV. And depending on the emittance, you can see it has plotted for various emittances, but I want you to concentrate on the red curve, which is for 10 microns, and I don't know what that color is, I'm going colorblind. It's like a reddish curve at 12 microns. And you can see the spot size variation as a function of energy. If you just vary the emittance by 2 microns, you can actually meaningfully measure. And therefore, you have diagnostics to tell that how much emittance growth you're getting. Next one, please.
Yep.
Okay, so what are the sources of emittance growth? Well, the sources of emittance growth are, even if you design a perfect ramp, you could have error in positioning the beam waist in the plasma matching section. You can have error in the ramp density profile for the matching from ideal profile that you need. The bunches actually have a finite energy spread, and they have asymmetric emittances in complex phase space, so that can screw you up. And so we need to incorporate all these effects into PIC code. For now, we make estimates using the Courant-Schneider formalism that I talked about for ideal beams but non-ideal matching. Next one.
Yeah.
Okay, so I just want to show you one example of effect of errors. Suppose we make an error in positioning or focusing of the beam at the beginning of the ramp. So there's just too much information here, but concentrate on top left frame, which shows sigma, which is the spot size of the beam, versus Z. And there are two curves here, two parabolas that are shown. One is the vacuum spot size, which is the solid blue, and here's the error, which is dotted blue by just by 2 centimeters. And you can see that when you do it properly, which is the solid blue, then when the plasma is there, the beam envelope adiabatically shrinks down and then gets matched to the plasma which is the pink line. And if it is not matched, which is the dotted blue line, the beam envelope shrinks down, but then begins to oscillate up and down because there's betatron oscillations. And so it's very fortunate because we have a diagnostic for measuring whether we are matched to the plasma or not, very sensitive diagnostic, because any mismatch leads to betatron oscillations of the beam, and therefore betatron radiation emission of X-rays in the forward direction that we can measure, and we can minimize this radiation, and then we know we are matched. Here is an extreme case. Next view graph, please. Hello?
Yep, done.
Okay, next view graph, please. Okay, this shows basically what happens if the density scale length is varied. So these are incomplete gamma functions of different orders, but basically they can be characterized by density scale length. And basically, if you have the perfect matching, then you get this beam spot size coming down, green curve, and matching adiabatically without oscillations in the plasma. And if you make a mismatch, slight mismatch, it's not very much, then you can see the beam envelope is going to do these wild oscillations, and therefore we'll have betatron emission, strong betatron emission from the plasma. I just want to say one thing, plasma physicists in general are not used to this level of reproducibility or accuracy or requirement on precise plasma conditions. But if you're going to build a collider, one has to do it, and we're going to have to do it. That's all there is to it. Okay, so we're going to have to know that we can produce the same plasma profile every time, and we can match this beam precisely. All right, next view graph, please.
Yep.
Okay, so this again shows another error, which is departure from ideal beta star. What happens if your focusing optic simply produces different Rayleigh lengths of the beam at the entrance of the plasma? Same thing. If you have any mismatch, it produces betatron oscillations. Next one, please.
Yep.
Okay, so all these errors are shown, summarized in this view graph. So departure from non-optimal matching conditions. Every time when there is an error, the spot size becomes larger in the plasma. And as a result, the beam oscillates at the betatron wavelength and emits X-rays. So there are three things shown here. These are errors in position of the waist in the ramp, error in scale length of the density ramp, and error in beta star. All those I showed you. But here, basically, the results are summarized, and you probably can't see the actual numbers very well. But it's a very important kind of calculation to make, to have an understanding of what level of errors you can tolerate and what you can't. Okay, next view graph, please.
Yeah.
So taking all this into account, because all these calculations were done, they're numerical calculations, but once we knew how to design these ramps, those ramps were imported into QuickPIC simulations with matching ramps for both the input and the output. And here is the result. You can see the plasma density profile, and there are too many parameters for the drive beam, trailing beam. You have my view graphs, and you're very welcome to share them, and you can study the parameters. And next view graph, please.
Yep.
Oh, no. This is a movie, and it's a great shame you cannot see it, because what it shows is now with the ramp, you can see that if you match with an external focusing optic at the beginning of the ramp, then the beam comes into the plasma and remains at its equilibrium, match spot size without any oscillation. And in fact, let's go to the next view graph, because that summarizes what happens to the emittance.
Yep.
Okay. This one shows the emittance, the projected beam spot size and emittance. And you can see that the spot size, which is the red curve, at the beginning of the ramp, the spot size is 6 microns. As it comes in, the beam is focused, and it becomes more or less a constant spot size. And as it escapes, again, the beam is becoming large. At the other end, you got two ramps. But the main thing you notice is the emittance, which is the blue line, the normalized beam emittance. At the input, it was 10 microns, input of the ramp. And as it entered the plasma, it is still 10 microns, and it exits the plasma at 10 microns. In other words, it is possible to do an experiment where there is no emittance growth of the beam. And let me just give you some idea. Such an experiment has never been done with either beam-driven plasma Wakefield accelerator or laser-driven plasma Wakefield accelerator. And everyone who's doing laser-driven plasma accelerator, if they are interested in doing it for high-energy physics or FEL applications, will eventually have to deal with this issue. And so it is an important thing to realize. Okay, I'm going to try to finish in 45 minutes. Okay, conclusions. So our goal is to demonstrate full pump depletion, doubling of energy, little or no increase in energy spread of the beam and emittance, and a 50% beam-to-beam energy transfer efficiency, all at the same time in a single experiment, because we want to demonstrate that beam parameters that are relevant to a staged plasma accelerator for a linear collider are realizable. And the DOE is prepared at the moment, at least. I don't know what the new administration is going to do, but the DOE is prepared to give us 10 years to do this. So we believe we can do it. So lots of careful work is needed to make the plasma source with precise ramps and reproducible ramps. They can't vary from shot to shot. And it has to work at 10 hertz. And at the same time, the facet facility has to deliver the drive and the trailing beam, which have exactly the same parameters every time, and beam focusing optic that will accurately focus those beams without jitter in the same position with the same spot size. We think that with the lithium oven source that we've been using in the past, we can design such ramps, and we can control such ramps by several techniques, which are all engineering techniques that I don't have time to go into. And there's some modification of the ramp due to ionization and energy spread arising from non-optimal beam loading that are the biggest dangers to emittance spread. So we are expecting, which are some of the effects that are not included in QuickPIC simulation, but those effects could increase the emittance by tens of %, which we can measure. So with that, I think it's almost exactly 45 minutes. So I will stop and I will take any questions if you have. Thank you.
Thank you, Professor Joshi. The talk is open for questions or comments.
Joshi, I'd like to just ask you that the PIC simulation, so the space charge is taken into account?
Yes, of course. Of course, it is taken into account. It's just that with 20 or 10 GeV beam, the space charge is not that important, because the magnetic field and the electric field of self beams of the beam itself cancel out to the order 1 over gamma squared, no, to the order gamma squared. So, so they're almost equal to each other.
Chan, this is President Kao.
Yes, hi.
Hi. What are the challenges in positron acceleration? You didn't describe that too much.
Right, I didn't. It's a whole whole talk, the challenges of plasma accelerators, the positron acceleration works. Positron acceleration works at high gradient, high efficiency, narrow energy spread, everything. But the prospects of maintaining beam emittance straightforwardly are very dim. And the reason for that is we don't have the field structure of the longitudinal and transverse fields in the wake is highly nonlinear. And as a result, the beam particles gain energy and do betatron oscillations with different phases at different longitudinal and transverse positions. And so there's a phase mixing that goes on, which leads to emittance growth. So the one avenue that we are pursuing is positron acceleration in a hollow plasma channel. In a hollow plasma channel, there are no focusing forces, and the accelerating field is uniform in the transverse direction. So all the particles in a one given longitudinal slice gain energy at the same rate, and there's no focusing force. So that's a problem, because that means you can propagate a beam only one Rayleigh length. But on the other hand, you can put external magnetic field to keep the beam focused. And so we've done a considerable amount of work on hollow plasma channels, and some of it is published and a lot of it is not, but it'll be published in the next year or so. But there is no scenario for proper beam loading in a plasma. In a hollow channel, there is.
Hi, Chan. Very exciting to see all this. But the facet to what would be you said it's a 10-year program. So you're going to push
Yes.
the energies, or you're going to push the overall beam characteristics? What would be the main thrust there?
The main thrust is we're not going to push the energy. We've already gained 9 GeV energy, okay? So it's not the energy. What is important is we take a 10 GeV beam, deplete it completely of its energy. So most of the particles go down to 0, okay? And transfer that energy to another 10 GeV beam, sending it to 20 GeV, and demonstrate that 50% of the energy that was contained in the wake has been extracted. Okay, so high energy efficiency and energy spreads that are less than 1%. And main point that people, I think nobody will be satisfied until we show that, is that the emittance of the beam can be preserved. There's no growth of the projected emittance of the beam.
So the efficiency of 15%, I mean, I was struck by the contrast.
50.
50, yeah, I was struck by the contrast you made with the CERN, the other colliders. So this seems like 4 orders of magnitude larger.
Right. So such is the problem or challenge in front of the future linear collider, that the net efficiency has to be 10%. So the accelerator efficiency is 50%, but then we are using a beam. So that beam has to come from traditional accelerator that is low efficiency. Okay?
Yeah.
So, but there are ways of producing beams with 30% efficiency.
Number has to be 10%, so the actual temperature is 50% here in the seal.
Okay, thank you.
Thank you.
Right.
I have a question.
Yeah.
Yes, me. As QuickPIC code based on quasi-static approximation, then how do you separate these two beams evolution?
That's a very good question. So, so evolution of the beam over a betatron wavelength is relatively small. I mean, I can't, you'll have to take my word for it for now, okay? So this approximation is pretty good. What we have done is we have benchmarked the QuickPIC code against full relativistic electromagnetic code OSIRIS, and shown that the fields and field evolution it gives are highly accurate. I mean, accurate to better than percent. Now, the beam evolution, particularly the front of the beam, is a little bit different in OSIRIS compared with QuickPIC, but not sufficient to affect the wake.
What beam size will be good? I mean, transverse size to longitudinal size. The ratio of the transverse size to longitudinal size of the driving beam will be good for the acceleration.
Right. So that's right. So you can see these beams are like pencils, right? So and it's purposely that way. The length is longer than the diameter because the front of the beam is etching away, and you want enough beam left so that it propagates the entire length of the accelerator.
Thank you.
Any other question or comment?
I realize that this is a very specialized talk, and also most of you are interested in laser Wakefield acceleration or familiar with laser Wakefield acceleration. But I really thought I'd give this at the end of your week-long workshop to show you, what level of challenge there is in the future, and eventually one has to face them.
There is one more question.
Sorry, a quick question. So, why are there just two bunches? Could one actually scale even that up?
Well, I'm sorry, I didn't
There's
understand.
a leading and the trailing bunch. Could you
Yes.
have maybe another bunch and try to get more out of it, or is there some limiting reason for engineering it this way?
Oh, okay. In traditional accelerators, the amount of energy extracted by the accelerating bunch is so small from the accelerator that it is possible to put multiple bunches, 10, 20, 30, multiple bunches in many buckets, accelerating buckets, and eventually extract all the energy or much of the energy. Okay, that is the idea in the future linear colliders. In plasma accelerators, you have to do it in one shot for the simple reason it is only the first bucket that has the electric field structure that is clean enough and the structure that is robust enough, that is indestructible enough, that you can extract the energy. And as soon as you put one bunch with sufficient charge, it already depletes the electric field for all the behind it completely. And so all the energy just comes out in one. There is no reason for putting two or three or multiple buckets, multiple charges.
Thank you. Is there
All
any other
right.
question? Otherwise, I would like to ask a question. It is a sort of long shot question coming from a high energy theoretical physicist.
Sure.
I mean, if you choose to do, I don't know whether you will like to answer it. I want to ask, suppose we want, let us say, 100 GeV laser plasma accelerator for real high energy physics experiments with good emittance, good energy spread, and so on. What do you think is the time scale? Is it
I think 100 GeV.
Yeah, let us say 100 GeV. Yeah, 100 GeV. Let us start with 100 GeV. 100 GeV, but a usable beam, usable by high energy experimenters.
Yeah, right. So
When will that happen?
Right. So, well, it won't happen for the simple reason the only accelerator that. Well, do you want electron positron or electron electron?
Let us say
or-
electron positron.
Okay, so the reason why it will not happen is because the only accelerator that would act as a drive beam, okay, for plasma Wakefield accelerator, that is beam-driven scheme, is the Stanford Linear Accelerator. And unfortunately, that lab has transformed over to a free electron laser lab. So no 50 GeV drive beams exist anymore. But if you had a 50 GeV drive beam, you could accelerate another 50 GeV drive beam to 100 GeV. And in fact, we had made that a proposal in early 2000s, but we hadn't at that time made amount of progress that we have now to justify it. Now, as far as a laser plasma accelerator is concerned, honestly, in my opinion, and it's my personal opinion, the state of the art is at least a decade behind compared with the sophistication of the plasma Wakefield accelerator work. And so on the face of it, it looks like 4 GeV energy gain and energy spreader and all that, but the reproducibility, reliability, all this stuff, and and is a long way to go. Because of the also phase slippage problem in laser plasma accelerator, energy gain per stage is likely to be limited to less than 10 GeV. So you need at least 10 stages. And staging has all these problems that I talked about of matching and radiation emission due to mismatch and all this. And so they're going to have to solve those problems as well. I don't know. You had a talk from Bella, right? And did they mention any of that? So
it's actually tomorrow, so we'll hear.
Oh, you'll hear tomorrow. So yeah, I think they have to do the same thing, and it's a tough problem.
Thank you.
So the answer, in short answer, is that the lasers to produce 100 GeV exist. The lasers to produce the required luminosity at 100 GeV can be probably built. Lasers to produce a TeV in center of mass don't exist. Okay, and the required luminosity don't exist, and at the moment are not economically feasible either. But 100 GeV, maybe they are, because the luminosity goes as gamma square. So it's that much lower at 100 GeV. So I would say that, but there is much work remains to be done.
Can one say that considering the fantastic progress which you people have made in the last 20 or 30 years, it might happen that similar progress will make it possible to really get there even before I mean, maybe one can have an optimistic view. I mean, that is what I want to ask you. And
yes.
Considering the way your field has progressed, you people have made progress, it's quite possible that that maybe not in the immediate future, but not in the distant future either. So it might happen.
Yes, well, by the way, this DOE strategic plan equally holds for beam-driven accelerators or laser accelerators. So in a sense, the Bella people are going to have to show pretty much the same thing in 10 years. So they may very well do it. I mean, there's a real direction which is agreed by the community, that is us. That this is the next big issue and has to be solved. And so in the next 10 years, we might very well see one stage of a plasma accelerator and then learn to multi-stage it.
Thank you. So thank you very much, Professor Joshi, for this excellent talk.
All right. Thank you all.